And the camera is selecting that, right? Yeah, but this is yeah, like that. And yes, sir. Right. Oh, yes. Yeah. This one, right. Oh, why? 1221. It's right now in 2. Connect. Yes, sir. And let's check the let's check or okay, and these are YouTube too, right? YouTube 90 already. Yes, it's go live. And let's check for manage. Just a smaller, and just get to this one. It's not made for kid. Yes, alright, it's not entertaining, it's education, like that. Open widget, yes, and let's see what. Okay, this one is small. Oh no. Right, and yes, sir. Right. We are gonna be closer. Right. Yes, sir. Alright. Is that thing alright? Yes, sir. And then what else? This one. So go. Not in close screen. No. version. But for this one, we would stay in a bigger scale like that, like bigger scale, even bigger. Maybe just close this one and use the Firefox instead. But we'll use the Firefox and close this one. Use the Firefox instead, right? And yes, and the microphone could be higher if you want, right? It's just stay above like that. Okay. All right, and you. Stop. Let's open video. Error. What I don't understand is it's reconnected to one couldn't see right here. Right. Let's see the CPU performance. It's almost 100%. Memory stop. Oh. Oh. Yes, sir. Use this one. Yes, sir. All right. Feel it already. It's 40 actually, right? We still have 10 minutes. Right. We still have 10 minutes in we say the 3. Yep. 84 right now, and stop this one, right? Otherwise we wouldn't have enough internet bandwidth in stream health. Let's see this site. 1231. Oh, it's in let's open the no, not this one. A solid liquid, right? For both 605. This one, right? Let's open. Okay. Ideal fluid. Okay. It's like that. Yes. The left one and the right one. Yes, we can open it like this, right? Okay. 3. Right, and what else? Testing outside. Okay. Okay, today we will talk about ideal fluid and continuity equation. Next one is the Bernoulli Equation. There's the Bentley Equation into this one. Right. Okay. Ideal fluid first. Our page up. Oh. Yes, star right here, the content in this star. fluid dynamics, right? Okay. 36. It's 36. Following. Okay, test the sound, right? We're gonna test the sound. 1, 2, test 1, 2, 3. Okay. And another channel, right? We don't have the machine. I hope that let's check the okay, test 1, 2, 3, but the sound is not there, right? So let's look at the sound tone, right? I'm gonna show me, right? 1, 2, 3. Okay. Yes. Good morning, everybody. Everyone. Welcome you to SCI33206. Today I have plenty of time, so everything is quite perfect. And yes, we have again. We have, as usual, right? 3 channels. I'm gonna send you the possible link. Okay. The first one is right here. The second one, the third one, right? It's up to you, okay, which channel you prefer. And line M604, right? This one, right? Yes, the second link is this one. Okay, and the third link is this one, right? M604. Okay. Yes, for M605 later. Okay, we're gonna see it later in นภัสพิมพ์มาแล้วนะนภัสนะครับ and let's take a look at this. Okay, yes, yes, the topic today, actually we have started already this topic. The topic today is the ideal fluid, right? We have started last time, and the next one is going to be continuity equation ภาษาไทยเรียกว่าสมการต่อเนื่องโอเคครับ and the third topic in this section, right, fluid dynamics, right, Bernoulli's equation, which is the last topic in this section. Okay, this section is fluid dynamics. Okay, you have seen everything about fluid, and we have calculated or considered several situations for the fluid, but it's in the static, right? There is no movement for that fluid at all, right? Yes, and you have seen previously the movement, right? Or sometimes it's called in formal way, it's that's the dynamic, right? The dynamics or the movement of the fluid, right? Yes, in this section there are three subtopics: the ideal fluid, okay, which is what we are going to talk about, and the next one is continuity equation. Okay, we have here we will talk about the basic property of the ideal fluid, because the realistic fluid is quite hard, okay, to capture every detail, every phenomenon, and we will assume that the fluid that we will go ahead is or follow the ideal fluid, and we have the first relation, which is called continuity equation, and the one which includes several effects, okay, also the potential energy or the pressure, it's called Bernoulli's equation, and then we will finish the first chapter of this semester, which is actually the 5th chapter. All right, okay, I didn't monitor you by headphone. Okay, okay, I'm going to wear the headphone. If you have anything, just let me know. โอเคใช้สิทธิ์พิมพ์ที่ซูมมานะครับ1คนครับมีใครจะเข้าอีกไหมครับผมพยายามชำเลืองนะครับ Okay, yes, in this chapter, in this topic, we have already started yes, as we know last time, right, the ideal fluid has several ideal assumptions: no velocity change, no density change, no pressure change at each point with time, and it just moves without any turbulence. It means that turbulence is somehow like circulation, right? It means that there is no angular velocity at all, okay, around its center, and we may also treat the gas as incompressible, but it's not the truth, right? It's not the fact. The pressure difference from one region to another is not too great, okay. We just assume or take this assumption, and in some cases the shear forces of two adjacent layers are negligible. It means there is no viscosity or viscous force in comparison with forces arising from gravitation and pressure difference. Okay, we pay attention mainly to gravitational force and pressure differences. Okay, pressure differences between two locations, two regions. Okay, a flow line in the path of an individual elements of a moving fluid. Okay, let's move to this one. We will move to let's move to, where is that? Okay, right here. A flow line, right, is the part of individual element of a moving fluid. Okay, and steady flow is the overall flow pattern that does not change with time. Okay, the ideal fluid has a steady flow. Okay, and laminar flow is the kind of fluid flow when adjacent layers of the fluid slide smoothly past each other, and turbulent flow is a kind of the fluids too, right? And when the flow becomes irregular and chaotic in turbulent flow, there is no steady state pattern because the flow pattern continuously changes. Okay, changes with time. Okay, but Thailand sorry. Okay, and who else? Yes, the next one. Conservation of mass in fluid. Okay, flow gives us an important relationship. Okay, we start now the next topic, which is called continuity equation. It's called the continuity equation. Continuity equation expresses the conservation of mass for an incompressible, okay, the fluid that cannot be compressed. For an incompressible fluid flowing in a tube or some other channel or tunnel. Okay, and yeah, let's go to the figure of this continuity model. You have here pipe, right, or the fluid tunnel or channel, right, and the fluid cannot be escaped. Okay, cannot escape out of this region. Okay, this is the closed area, and yes, the fluids flow from the lower location and it goes up here, and the cross-sectional area, which is denoted by A1 and A2, okay, for the lower part, and the upper parts are not different. Okay, the cross-sectional areas at both locations are not the same, and flow in a tube with changing cross-sectional area. Okay, the flow starts from A1, okay, and A1 is not A2, it's not equal to A2. Okay, so A1 is not the same value as A2, and you have lower cross-sectional area here, A2, and if you take a look at the tiny parts of this movement, okay, for a small amount of time, it's denoted by delta t here, and at this location it has the speed v1, and at the upper location you have speed of v2. Okay, and yeah, because here you have greater cross-sectional area, you have less cross-sectional area, and of course you would guess that in nature you would have greater speed v2 here, right? V2 should be greater v1, right? Because you have strict or confined area here. Okay, and yeah, if we take a look at the thickness here, the thickness is gonna be the distance, right? The distance. So v is the speed, the velocity with the distance with time, distance divided by time, and you multiply it by a small observation time delta t, and you get the distance back here, and that's the thickness. Okay, you have v2, which is the speed at this location, and you multiply it by the time of observation, a tiny amount of time observation. You get v2 times delta t, which is the thickness of the second location. Okay, and the continuity equation, this is the figure or the model taken from the book number 2, and here is the same thing. Okay, it's the same model, but it's taken from book number 1. You have delta x1, and which is the distance, right? And yeah, if you want to find the relationship between v1 and t here, right? The relationship between these two figures, you would see that delta x1 is actually v1 delta t, right? And in the same manner, you have delta x2, okay, which is the thickness at the upper location is going to be equal to v2, right? Delta t also, right? Yeah, if you observe this fluid movement for a small or tiny amount of time, delta t, you get the same thing, right? And there is some volume of fluid here. Okay, you have also here vector v1. Okay, this is represented in terms of vector. You have vector 2, okay, in this direction, and you have a2, the cross-sectional area at the second location. You have the a1 at the first location here, okay, and the volume flow rate, okay, continuity equation says that the volume flow rate through a1 must equal the rate through a2. So a1 times v1 equals a2 times v2. Okay, this is called because this is the volume, right? It's the speed, or it's the flow rate, right? Flow rate, it's volume per time, so it's the flow rate. Flow rate at the first location is equal to the flow rate at the second location. Okay, but this is valid for the ideal fluid. Okay, because you know that if you let the fluid flow in a small hole like this, you would have more friction, right? And yeah, the speed here may not follow exactly this equation, but anyway, we just learned something about theory which is suitable to you in the high school level or the secondary school level. We don't have any integration or calculus in this location at all. Okay, for you in the high school level is gonna be a1 times v1 and a2 times v2. That's the continuity equation. Okay, yeah, that's the flow rate, as I told you. It says that the amount or either mass or volume of fluid flowing through a cross-sectional area of the tube in a given time interval delta t. Okay, cross-section means the A1, A2, right? The cross-sectional area must be the same for all cross sections. Okay, whether you observe it here as the first location, the second location, or even you observe it here in the middle as the third location, you got the same. You will get the same relationship here. A1 V1 equals A2 V2 and equal A3 V3. If you observe it right here, yes, it's the flow rate, which is the change of volume that fluid flows per time. Okay, the time of observation. Anyone else มีใครเข้าที่ซูมไหมครับมีประธานินกับชัยสิทธิ์2 คนนะครับ Okay, in 95, in this equation, the product A times V is the volume flow rate, as I told you here. Because you know that V is S by T, right? Or distance, and A is the cross-sectional area. So A and V is going to be S times A divided by T, which is actually delta V by delta T. Okay, that's the same thing. Okay, yes, S and A, right? A is a square meter, S is meter, right? So it's got to be cubic meter, and that's the volume, okay? Because the volume has the unit of cubic meter. Now you know something about continuity equation. This is the representation in volume flow rate. Okay, this is the expression in terms of volume flow rate. In if you go further, there is another form of the continuity equation. It's called mass flow rate. Okay, but this one is not quite popular to this one, right? This is the basic formula, and here is a more sophisticated formula. This is the delta of volume per delta T, delta time, right? And here is the delta of mass, and the difference of the difference of time, and of course this is the volume, and from the basic definition, density is the mass per volume, right? So you just multiply both sides. You would get here the delta. Multiply this equation on both sides. Okay, multiplied by rho. Okay, then you get mass per time, right? If you multiply here mass per delta V, right? Delta M per delta V, you can get cancellation of this one and this one. You get delta M by delta T, and here delta M by delta T is actually the density, right? Which is rho. Okay, the density of that fluid, you get also rho at the right hand side, and you get, and that's why we get this expression here. The product of three terms right now, the density of that fluid, the cross-sectional area of the pipe in whatever location, okay, in wherever you want to determine or use the continuity equation. And the last one is the speed of that fluid, in that location. Okay, you get you have got to know, you have known that there are three forms of the continuity equation, okay, which is the topic of this section, right? The first one is volume flow rate. Okay, it's the unit of the volume flow rate is cubic meter per second, right? Here is cubic meter per second. Okay, and the unit for the mass flow rate is, what is that? It's kilogram, okay, per second. Okay, yeah, it's a little bit different from each other, but they follow from the same idea, right? The A1 V1 is equal to A2 V2. Okay, and you just multiply this form, okay, by the density of that fluid, you get this one. Okay, now we arrive at the first example about the continuity equation. Each second, okay, in each second, 5,525 cubic meter of water flows over, where is that? Okay, this one. I hope that you could see it, right? ที่ซูมจะเห็นไหมซูมจะไม่เห็นเนาะ where is that let me check the hello test โอเคก็เสียงก็โอเคโอเคyes the ที่ซูมจะเห็นไหมเนี่ยokay in the zoom channel here we are at the Niagara Falls. Okay, I don't know, I have never been in the in this location. Okay, I have been in Canada, but I have never been in the United States. Okay, okay, at the Niagara Falls, there are two falls. The first, I don't know how many falls do they have in that location, but one of the falls region is called horseshoe. Okay, the horseshoe, the shoe of the horse, I don't know, falls, and the length of the brink, okay, in this way, the length is 323.08 meters. Okay, it's less than 1 kilometer actually. Okay, the height of the water is 21.3 meters. Okay, if you measure it from here to this location, I don't know. Okay, if you measure the height of this waterfall from this location to the base here, it would take 21.3 meters, and if you measure it further downward to the ground of this area, is going to be 53.6. Okay, inside this water there is the depth of the difference of this value. Okay, what is that? 32.3 meters. Okay, and the flow rate of the water is 511 liters per second. Okay, it's the data from this website, but in our problem we have 5,525. Okay, you know that if we divide this value by 1,000, it's gonna be the cubic meter, right? So yeah, almost the same value, right? Is that correct? 1 liter is 1,000 liters is the amount of 1 cubic meter, right? So the data from the problem is 5,525 cubic meter, and the white cliff, which is the distance here. Okay, white cliff is 670 meter. Okay, the horseshoe fall portion of the Niagara Falls นะครับใครไปอเมริกาก็ไปเที่ยวดูได้นะครับผมไม่เคยไปนะครับโอเคไหมอเมริกานะครับ so unfortunately the water is approximately 2 meter depth. Okay, it means if you measure the water here, the water level to the ground at this location is gonna be 2 meter. So we have basic model like that. We have the height here 2 meter, right, and the width here, water cliff, as 670 meter, right, right here, and yeah, it's just flow. This is the cross-sectional area, cross view of the waterfall flow, right, and estimate its speed at that instant. So yes, they just ask you what is the speed of water flow in this at this location. Okay, what is V? And as we know that the water flow rate is this value, right? Let's draw something on this page. Okay, the water flow rate is that value, which is the 5525, okay, in cubic meter per second. And what is that? Water flow rate could be expressed as the mathematical relation, like it's delta V by delta T, right? And from what we have just learned in equation 96, okay, we have here delta V by delta T is AV, right? Is the product of our cross-sectional area and the speed at that location. Okay, so what they want to know is the speed, right? They want to know the water flow or the water speed before it falls down, okay, to the lower layer here. What is V? So we need to solve this equation for V. So V is gonna be 1 by A and delta V by delta T, right? So it's actually delta V by delta T divided by A, right? And you know that delta V is the water flow rate, this value, right? And we know from this model that from this diagram that cross-sectional area is going to be width, right, times height. Okay, so it's going to be 670, right, in times number 2, right, and that's the 1340 square meter. So we get 1340 for the cross-sectional area. Okay, right now you have the water flow rate, which is 525 divided by 1340, right? 1340, and you put it into the calculator, right? 5525134 speed is 5525 divided by 1340, and you get the answer as 31231 of 4. Okay, you get somehow 4.1231. Of course, the unit is meter per second. That's the speed of the water flow. Okay, here the water flow rate is gonna be around 4 meter, right? Approximately 4 meter per second. And what is that in kilometer per second? Kilometer per hours. You have to multiply it by 3.6, right? 3.6 of this one. It's around 15 kilometer per hour. Okay, that's the speed of the water. That's quite strong, right? The water flow quite so fast, so quick. Okay, now we move to, is that all right? Yes, it's 4.1231, right? The next the next example is given 1 liter is 1,000 cubic centimeter, right? It's cm with the power of 3, right? Let's just 2 3 is cc actually, right? 1 liter is equal to 1000 1000 cubic centimeter, and a water hose, it's a water pipe. Okay, it's a kind of flexible water pipe, and the diameter of that water hose, the diameter of the water hose is 2.5. Okay, here the distance along this line is 2.5 cm, right, centimeter, and this hose is used by a gardener to fill 30-liter bucket. Okay, a gardener, this guy, just carry the water hose. He has a water hose like this. Okay, and that's the inside of the water hose, and he has the container which is called bucket, right? Bucket. And yes, the water is gonna flow from this hose, and he wants to fill this bucket in with 30 liter of water, right? And the gardener notices that it takes 1 minute. The clock say, okay, the clocks are said 1 minute of time, and the water is completely filled in here. The water is right here. I'm not sure with an opening of cross section. They didn't use the simple hose like this. They have also something smaller, right? That has the smaller cross section. It's 0.5. Okay, square centimeter. Okay, this is not the pure hose. Is then attached to the hose. Okay, this is the first scenario. Okay, in the second scenario, the same person, the same gardener, carry this hose, but he, I don't know which reason, but he filled in with not so. Okay, not so means a device that provide less cross-sectional area, right, in the same container bucket. And yeah, the cross-sectional area of the not so here is a not so is 0.5 square centimeter. Okay, the cross-sectional area of this not so is 0.5 square centimeter, and the not so is held so that water is projected horizontally from a point 1 meter below the ground, and over which horizontal distance can the water be projected. So it's a complicated problem actually, this one. Okay, ช่างถามได้ยากนะครับ okay man. They didn't leave the bucket at all in they just say that the water flow in horizontal way, and of course this would follow the projectile motion, right? This is the as you learn in มัธยม 4, it's projectile motion, right? And they want to know the distance here. what is distance at this motion that can be travel along the x-axis here. Okay, and the height is 1 meter above the ground. Okay, the height at this location is 1 meter. Okay, all right. So they just want to ask you how far the water is going to reach the ground here. Okay, this is the floor of the ground. All right. So yeah, any idea from you who could solve this? ผมก็ไม่มั่นใจว่าผมจะแก้ได้หรือเปล่าครับเพราะว่าปัญหาก็ซับซ้อนเหมือนกันแม้ว่าจะเคยสอนมาแล้วแต่มันก็ลืมครับใช่ไหมokay that's the first stage. Okay, let's summarize what's going on here. This is the first stage. Okay, the second scenario here. Okay, let's start from the first scenario. In the first scenario, okay, what we have learned is only the continuity equation, right, which is the a1 v1 equal a2 v2 or delta m by delta t is equal to rho av, right? ขออนุญาตแคปเจอร์หน้าจอรูปคุณสักหน่อยนะครับเพราะว่าเดี๋ยวเผื่อเป็นอะไรนะครับอินเทอร์เน็ตเสียหายครับPetra until Thailand Petra and this one is the Petra until Thailand. This one too, right? We need to capture the first. Shortage. This. Okay. This one 3, 4, 3, and 2. Right. Okay. Finish it. Okay. Yes. In this problem we have two scenarios. Let's consider the first scenario, right? ประมาณนี้นะครับมันติดปาวินไปอ่ะเนาะปาวินเนาะคนที่3ของรูปนี้ Okay. In the first scenario we're gonna use the continuity equation, right? Yes, from what you see here, 30 liter per 1 minute, right? The clock just go for 1 minute and water is fulfilled in this bucket, so the water flow rate, okay, delta V by delta T, okay, will be 30 liter per 1 minute, okay, And yes, of course, if you convert it, 1 liter will be 30 times 1000, right? And that's the cubic square centimeter, right? And 1 minute is 60 seconds, right? And if you convert it to the SI system, right, it's gonna be 30 times 1000 times 10 raised to negative 6, right? It's cubic meter per, again, 60 seconds. Now let's compute this result, and it's gonna be here, right? 1 and number 2, right? It's equal to 5, right? It's 505 times 10 raised to negative 4, right? And cubic meter per second. Okay, so it's less than 1 cubic meter. Yes, it's somehow like that. Yeah, that's the water flow rate. We get a water flow rate from the first scenario. And now let's talk about the second scenario. Let's talk about the second scenario. We open the next page, right? And the second scenario is C. D2. Okay, in the second scenario, of course, we know the water flow rate. And one of the expression for and one of the expression for the water flow rate is the delta V by delta T equals A1 V1 A2 V2, right? And we are talking about the nozzle here, right, which has the cross-sectional area of the nozzle as 0.5 square centimeter. So it's A, right? A nozzle 0.5 centimeter is actually 0.5 times 10 raised to negative 4, right? Square meter, right? And it's actually 5, right, times 10 raised to negative 5 square meter. Okay, let's draw again the formula of the flow rate of the water. It's delta V by delta T equals A nozzle times the velocity at the nozzle, right? Velocity of the water at the nozzle, N ZZLE. Okay, and yes, we know these the water flow rate, right, from the first scenario. That's the 5 times 10 raised to negative 4 cubic meter per second. And A nozzle, the cross-sectional area of the nozzle here, is also what we know. We don't know the speed of the water at this location here. Okay, we are gonna we will move A nozzle to the left hand side so that we can get the speed. So V nozzle will be delta V, which is by delta T, that's the water flow rate, divided by A nozzle. And let's go ahead. V nozzle will be water flow rate, which is what is that? Water flow rate is 5 times 10 to the negative 4, right? And cross-sectional area of the nozzle is A nozzle is 5 times 10 that's to negative 5. Oh, sorry. Sorry for that. Right. So with this division, you would get 10, right? 10 meter per second อีกแล้วครับ ไม่รู้ว่าโควิดหรือเปล่า Okay, that's the speed of the water from the nozzle. ขออภัยครับ ถ้าพบกันนี่คงไม่ดีต่อผู้ปกครองคุณแน่นะครับ เขาจะกังวลนะครับว่าผมจามใส่หน้าคุณ Here the nozzle, and the water is gonna flow like this, and the horizontal speed Vx at this location is ขออภัยครับ 10 meter per second, but it's not something like that because we live here on Earth, right? There is gravitational force that try to pull the water down to the ground on Earth, right? So we get water flow in this way, right? The water is gonna flow like this, okay, and yes. The height here is 1 meter, okay, above the ground, okay. So what is the idea to solve this one when you know the horizontal speed? But yeah, how could we solve this one? นะครับถึงจะมีอะไรมากวนที่ช่องหายใจแต่ผมยังสมบูรณ์พร้อมที่จะไปต่อนะครับโอเคไหมwe have to think about this problem into two axes, okay, two domains. The first one is that we go let us let's consider the motion in the vertical way. Okay. What does that mean? It means the water, let's say this is a drop of water, okay, it has mass m. You know that it has only initial speed along the x-axis, that's Vx, right? But there is no initial speed along the y-axis at all in the vertical way, right? So the Uy, right? Uy is 0. There is no initial speed along the y-axis. Okay, and it moves to the ground, right? Let's consider only the motion in the vertical way. This is the ground, and it just go like this. And here is the final speed Vy, right? Which is what we don't know, and we also don't know the time that is used for this movement, right? We don't know also the time, but we don't know the final speed, but it's not what we want. Okay, or you can also see if you can also calculate if the question just asks you what is the final vertical speed of the water drop here. But our important factor is the time that is used from this point to this point, right, to 1 meter here. This is 1 meter, right, the height of the water drop. Okay. Now let's find the time for the water drop, okay? Actually, the water flow continuously. And let's find the time here. What is the formula we could use in this scenario in order to find T from Mathematics 4, okay, the physics in your Mathematics 4, you would have, what is that? V equal U plus AT, and what is that? V square equals U square plus 2AS, right? And S is UT plus 1 by 2AT square and something more, right? With these 3 equations, which one do you think, which equation is suitable to our problem here in order to solve for the time, the variable t here? Which one is suitable?คุณคิดว่าอันไหนเหมาะสมที่จะถูกนำมาใช้ครับสูตรไหนเอ่ย We would choose this one, right? We would take this one, right? Because we know the gravitational on Earth is the g, right? Which is the acceleration of any object, okay? When it moves downward to the ground on Earth, right? Because this is our planet. And in this scenario, uy is 0, right? Sy is equal to the height, which is 1 meter, okay? And uy, as we know here, it's 0 meter per second. And the acceleration here, acceleration is actually equal to d, which is approximately 9.8 meter per second square, right? And yeah, once you substitute all of these things, right, into this expression, you're gonna have on the left side you have h, right, and 0 and t, right, and plus 1 by 2 and t square, right? But you want to solve this one for variable t, right? It's gonna be 2h divided by t equals t square on the right hand side, and t is actually positive value of 2h by t, okay? And let's substitute these values 1 and 9.8 into this expression. It's gonna be 2 times number 1 and divided by 9.8, and you're gonna get the time spent for the water drop to reach the ground of the Earth, right? The ground of this setup, right? So let's move to the calculator. We have that, and t is equal to square root of 2 divided by 9.8, right? You can use either 9.81 or number 10, okay? It's up to you. In yeah, we would get 45175, right? 45175. 45175 a second, right? That's the time the water consumes to reach the ground on Earth, right? But here is the consideration in the vertical way, right? For the water drop, we need to find the distance here, right? The distance. What is the distance that the water reach the ground, right? So, yeah, because the water motion has both vertical motion and horizontal motion, and it takes exactly the same time, right? Because it's the simultaneous process, right? Mechanism. So yeah, dx, right? D or distance. Let's consider the motion of the water drop or flow, water flow along the vertical way, the horizontal way. Okay, yes. Oh no, what happened? Oh yeah. Yes. Because along the x-axis or in the horizontal way, there is no force that acts or exerts on the water drop or water flow at all, right? There is only a single force, which is the mass of the water flow along the vertical way, along the y-axis, right? And yeah, and that's why we need to use this expression, because it involves the acceleration. But along the x-axis, there is no force acting on the water flow at all, water drop at all. So there is no acceleration along the x-axis movement, okay? There is no acceleration. Along the x-axis. When there is no acceleration in that movement, we are going to use simply the formula V equal h by t, right? And V equal h by t for this scenario. What does that mean? It means d equals Vy, right? Vy times t, right? Because the water flow like this with the Vy speed, which is I don't know, it's 10 meters per second, right? There is no acceleration, and the time consumed is this value 0.45 blah blah blah. So in this manner, we are gonna have the expression as d equal Vy times t. Okay, and let's substitute Vy is number 10. Vy is number 10, and the time consumed is 0.45175 second, right? And finally, you would get the distance, okay, as the 4.5, okay, one digit further, 175. The unit is in standard. Oh no, not per anything. It's meter, okay? And that's the answer for this question. The water drop would take would takes 4.5 away from the origin of the nozzle, okay, allow 4.5 meter from the nozzle port here. All right, yeah, it's 4.517 blah blah blah. Okay, and that's all for continuity equation. Okay, we have finished it. Continuity equation. What time should I? It's 14, right? 14. We still have 22 minutes more, right? Yeah, we have completed the continuity equation. It's delta V by delta T equals A1 V1 A2 V2, right? The water flow rate is the product of the cross-sectional area and the speed of the water flow. Now let's move to the next topic, or which is it's the last topic in this chapter, and I didn't prepare the next slide, the slide for the next chapter at all. Okay, we would complete the lecture today at this topic. Okay, yeah. Bernoulli's equation, right? It's the name of Daniel Bernoulli. Daniel Bernoulli is a Swiss person. He is a physicist, and yeah, in 1738, he derived an expression that relates the pressure of the fluid to its speed and elevation. Okay, it depends on the speed and also the elevation. In Bernoulli's equation is sorry. Bernoulli's equation is a consequence or the result from energy conservation. Okay, his equation is actually comes from energy conservation as applied to an ideal fluid. Okay, for the Bernoulli's equation, you should know that we use the assumption of ideal fluid. If we consider the realistic fluid, okay, Bernoulli's equation is simple. Bernoulli equation is no longer here, right? We're gonna use something more complicated Bernoulli's equation. Okay, but for high school, we would use this simple form, okay, because we don't have enough knowledge about calculus, integration, and differentiation. To derive the Bernoulli's equation, we assume the fluid to be incompressible. Okay, it cannot be compressed. It is non-viscous. Okay, there is no frictions. There is no friction among several layers of the fluid, and the flow is in a straight way. Okay, it's non-turbulent. It's steady state. Okay, the speed doesn't change with time. Okay, this manner. Okay, and there are two major forms of the Bernoulli's equation. As I mentioned before, right? We have two forms of continuity equation. It's water flow rate form, the mass flow rate form, right? Here we have also two forms for the Bernoulli's equation. The first one is for any 2 points along the flow tube, P1 plus rho g y1. You know that this is the potential energy, right? It's like the pressure depending on that you have seen before, and here is the pressure that comes from the kinetic or the movement of that fluid, right? And the summation of three terms of pressure: direct pressure, the pressure coming from potential energy, pressure coming from the kinetic energy, and that's the total pressure at the first state, the first location, and here is the total pressure in the second location. Okay, everything is described by the subscript number 2 here. Okay, pressure to height at the second location, and the speed at the second location too, right? And the second form is quite simple. The summation of the total pressure remains constant. Okay, it doesn't depend on time. It's only a constant, and that's the expression for the Bernoulli. Okay, in both form. Okay, the Bernoulli equation states that the sum of the pressure P with kinetic energy per volume. Okay, that's what I said. This is the term of kinetic energy, but it's measured per volume. And the potential energy per unit volume too, right? Rho G Y has the same value at all points along the streamline. Okay, if you take a look at the motion along the tube, for any tube, the Bernoulli said the summation of the total pressure remains the same for the whole streamline. Before we go to the realistic calculation example, let's talk about the effect that we could see in the laboratory. The Venturi effect, okay, is quite popular for you at the high school or even in the scientist laboratory. Venturi effects is the situation when there is a decrease of the static pressure in flowing fluids with increasing flow velocity due to energy conservation. Let's take a look at this one. If you drill the hole here and put a barometer, a meter that measure the pressure, it has velocity V1 here, right here, and you get pressure P1. And here, when the pressure, when the fluid tries to go to the smaller side, okay, smaller cross-sectional area at the second location, okay, denoted by number 2, and it has cross-sectional area A2. And here at the beginning, we have cross-sectional area A1, okay, at the first location, first region. Here, the fluid has higher pressure, okay, because we could observe here that it has lower pressure, actually, sorry. It has lower pressure if you compare the needle on the meter of the barometer compared to the first scenario here. It has lower pressure, but the speed here, okay, let's take a look at the length of this vector. V2 has a longer length than V1, right? It means the speed here is higher. And you know that with this effect, you could use the Bernoulli equation for realistic device like ทำไมมันขึ้นอย่างนั้นครับ I don't know. Yeah. Okay, ขึ้นอันใหญ่เลยโอเคครับขึ้นอันใหญ่ครับ Okay, here you have more speed than this location, okay, but the pressure here is lower, okay, because when something increases, another is gonna be decreases like this, okay. That's the model from the figure, but if you take a look at the realistic device, you have high pressure here. Is the needle is pointing at the number 5, okay, whether it's is in bar, right, the black one, and the low flow velocity, okay, the flow of the air here is low, and here you have lower pressure. Is the needle at this meter points to something between 4 and 5, okay, it's less than here, which points exactly to the number 5. But here you have high flow velocity of the air, okay, air is a kind of fluid, right? Just increase in flow velocity, you have lower pressure, okay, related reduction in pressure. But if you don't believe this, okay, the meter gets stuck, okay, it can move, the meters are broken. Just take a look at this one, okay. This is the physical way of pressure measurement. Here the fluid flows from the left to the right. Here is low flow velocity, high flow velocity, right? And when we drill this hole, right, and we drill this hole and connect it to a pipe like this, and we leave a liquid, okay, which has a noticeable color in the red here, right? And because as we know before, this one has higher pressure than this one, and once we connect it from both ends, you could see that at the higher pipe, at the left pipe, you have higher pressure, and that's why the air or the pressure, the fluid, try to put this liquid down. And this one has lower pressure, okay, they cannot compete with this side, okay, they just let the fluid go up, right? And that's the way you could observe easily, okay, if you don't believe this one. But this one is very precise because you have the meters, okay. That's the Venturi effect, okay. And yes, Venturi effects can be applied in realistic life, like in the wing of the airplane. You have higher pressure here, but it's lower speed, okay, lower speed of the air, and you have faster air wind here above the air wing, okay. On top of the air wing, you have higher speed of the wind, okay, but here you have low pressure. Here you have higher pressure, and because of the higher pressure you have, if you multiply the pressure difference, you're gonna get the force that tries to lift the wing up, and the wing is attached to the airplane body, so the airplane is gonna go up, okay. And that's one way to explain why the airplane can fly, okay, above the ground or in the air, right? Venturi effect for generating the lifting force of the aircraft wings, okay. We left at the first example, but now the time is over, right? So I need to let you take a break, right? Anybody who didn't type your name yet, please type it, okay. ใครยังไม่ได้พิมพ์ชื่อก็โปรดพิมพ์มานะครับวันนี้ก็คง if you have any question, just let me know, okay. If you are unclear about anything, okay, just let me know. If not, we're gonna quit this lecture right now, and see you on Friday, okay. We don't have homework, right? We're gonna have again the homework on Friday. ใครยังไม่ส่งกันบ้างก็ส่งเสียงนะครับ แล้วก็ย้อนหลังนะครับเต็ม 0.5 นะครับผิด 0.5 นะกติกานี้นะครับโอเคนะครับก็สวัสดีครับบ๊ายบายครับสำหรับ M604 ครับ no 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 not yet ยังนะครับเพราะว่าเราเลิกที่14:20นะครับไปต่อนะครับจนถึง14:00นะครับผมผิดเองยังไม่เลิกนะครับขออภัยครับผมเบลอครับกำหนดการเขาให้เลิก14:20ใช่ป่ะเราต้องเลิก14:00นะครับยังไม่เลิกนะครับ M604 นะครับผมผิดเองนะครับเดี๋ยว Okay, let's continue our lecture today. I'm sorry for that. A near side 35 cattle rustler with his trusty 6-shooter, and fortunately for the rustler, the bullet misses him and penetrates the town. ยังไม่เลิกนะครับ M604 นะครับขออภัยครับคือผมดูเวลาผิดเขาให้เลิกที่14:00แล้วเราเลิกก่อนไม่ได้ Okay, at this problem, the bullet misses him and penetrates the town water tank, causing a leak in figure 68. Okay, here. Okay, you have this scenario. The water tank is like this. It just lays with the base right on the ground, and yes, the base on the ground, and this is the rustler, right? And this is the sheriff, and he put the gun right here, right? The piston just go straight, okay? It goes straight, but it misses this person, the rustler, the thief, and it just hits the water tank. This causes a hole like this on the right hand side. There is a hole here, and now there is a leak, right? Once there is the hole, the water that is kept inside this tank. Okay, the water inside this tank. The water inside this tank tries to get out of the tank, right? Because there is a hole. So the question just come. If the top of the tank is open, okay, it's open. There is no leak. There is not a closed area. It's open to the atmosphere. Determine the speed at which the water leaves the hole. Okay. Try to find the speed from this one, right? Speed at which the water leaves the hole. When the water level is 0.5 above the hole. Okay, 0.5 above the whole water level. So right here, it's 0.5. H here is 0.5. That's the hole, and here is the water surface level. Water level. It's 0.5 meter away from each other, right? That's the first question. What is the speed the water start to get out? Okay, and what does the stream hit? Where does the stream hit the ground? If the hole is 3 meters above the ground. So there are two questions, and oh no, my god. The first question is what is V1, right? Vx, okay, what is Vx, and for the second scenario, what is dx? Okay, what is dx? Once the water will flow down, right? And you know, if you draw the water tank like this, and there is a hole, right? Sorry. Here you have water and the water try to get out of this hole, right? And they want to know Vx at this location. Vx, what is that? And the water tank is above the ground, right? But this is the base, and the hole here is how high is that? It's 3 meters. Okay, here you have the height difference 3 meters like this. Okay, and yeah, of course the water is gonna fall down to this location, right? And the question is, what is the distance here, dx? That's the quantity for the second question, right? So how could we solve this problem, right? Of course, this is the example in the topic of Bernoulli equation. We're gonna look at the Bernoulli's expression. Bernoulli expression says that P1 rho G Y1 equals 1 by 2 rho V1. Can you see it? P1 plus rho G Y1 plus 1 by 2 rho V1 square equals P2 rho G Y2 and plus 1 by 2 rho V2 square, right? But where is the first location and the second location with subscript number 1 and subscript number 2 to this problem? Well, if you look at this, the first location is gonna be this one, okay? And the second location is gonna be this area, okay? So let's summarize. We would have the first location right here and the second location right there. Okay, let's use a different color. First location, second location. So from the Bernoulli equation, Bernoulli equation. At the first location, the input actually first. As the first location, we're going to use Bernoulli's equation. What is P1? P, pressure of the fluid here. Of course, it's going to be the pressure caused by the air, right? It's P ATM, I think. There is no P at all, okay? There is no P at all, and there is no P. We don't take into account the right P1 equal P2. Okay, let's actually there is the pressure caused by the air, but we just neglect it. Okay, but if you want to write it completely, okay, I'm gonna write the full version. Okay, P1 is P ATM. Okay, and P1 and rho G Y1. Okay. Y1 is 0, okay, because let's say this is the reference, okay, the reference level, and V1, what about the speed flow in this way? There is no there would be some value for that, right? Let's talk about the second location. ผมเลยเวลาแล้วนะครับ the second location ยังไงก็ไม่จบอะครับข้อเนี้ยก็ยังไงอะคงจบไว้เพียงเท่านี้แล้วกันเนาะเพราะว่าถ้าจะเอาจนจบข้อนี้ก็10 นาทีนะครับโอเคไหมมันก็เลยเวลาเบรกคุณนะครับค่อยมาต่อคราวหน้าแล้วกันครับก็เดี๋ยวมาต่อปัญหานี้ในครั้งหน้านะครับ okay we will continue this problem later in the next lecture on Friday okay so we start the first example about Bernoulli Equation see you on Friday สวัสดีครับบ๊ายบายครับ 1420. That's the kitty, the last person. Kitty pun, maybe. Kitty pun. Petra. The first person. Kitty pun. Yes. Kitty pun. First person. This one foot. Oh no. 3 and 2. Right. $14.90. Yes, sir. Okay, good afternoon, everyone. Welcome you to SCI ก่อนมาแล้วนะครับ SCI 33206 right. This is for M605, right? M605 in. I'm gonna open the file for the people M605, right? Let's yeah, right here. At the first page, right? Okay, everything is alright. Oh,ผิดกล้อง Why not camera? Okay, the wrong camera. I'm sorry for that. Yes. Welcome you to SCI 33206. This is the section for M605, right? Yes. We live at the story about ideal fluid, and if you take a look at the content of this chapter, right, we reach here the fourth section of this chapter, fluid dynamics, right? You have seen already many stuff about fluid static, right? When the fluid just stay constant, okay, it doesn't move at all. But at this section, we will talk about the fluid that moves and the basic background in order to see several story in this section. Is the it is something about the ideal fluid. Okay, it's the ideal condition for the fluid in. Oh, somebody. Is there somebody else who wanna? Okay. The fluid dynamics, right? It's the movement, the story about movement of fluids. Yeah, after the basic background about the ideal assumption. For the fluid, we will talk about continuity equation, right? Continuity equation. It's the expression that shows relation between continuous flow of the fluid. Okay, we have the flow rate is constant, continuous in the whole line of the fluid pipe or the tunnel or the channel of the fluid flow. And in the last topic in this section, it's the Bernoulli Equation, which was just started in M604. It's the story about the equality that holds for the summation of the pressure at the first scenario, first case, or the second case. Okay, and that's it. Yes, we. Okay, this one is too far. Right? We will talk about this section, ideal fluid continuity equation and Bernoulli's equation in this lecture, but we could not complete. We would not be able to complete all these three topics as we have seen before in M604 ใครจะเข้าที่ซูมนะครับโปรดแจ้งผมนะครับถ้าผมไม่เห็นก็ขออภัยด้วยนะครับชวินนี่ M604 right yes now let's talk about our story the ideal fluid right yes the ideal fluid has no velocity change, no density change, and pressure change at each point with time. It moves without turbulence. Okay, there is no circular movement. Okay, circulation. It means it has no angular velocity about its center. Right. I need to send you the link. Right.ผมต้องแชร์ลิงก์ให้คุณเนาะแชร์ M605 share M605 share it to M oh no M605 right ไปไหมครับ3ลิงก์นะโอเคyes ปานทรปานทรกับปานธนะคนละลิงก์กันโอเคwe would need to know some basic things about fluid. A gas is considered to be incompressible. It means the gas cannot be compressed in this scenario, right? Which is not true at all, right? แบตเตอรี่ของมือถือนะครับมีปัญหานิดนึงครับกดก่อน All right. The gas can be considered an incompressible matter, but it's not true. And the pressure difference from one region to another region is not so much. Okay, we can neglect it. And in some cases, the shear forces of two adjacent layers are negligible. It means we would neglect the viscosity. Okay, we don't pay attention to the viscosity, which is the friction among several layers of the fluid. We don't care about the pressure differences at two different layers too. And basic thing in fluid flow is the following. The flow line means the path of an individual element of a moving fluid. And what is the meaning of steady flow? Steady flow means the overall flow pattern doesn't change with time. Okay, the flow pattern doesn't change with time, but it's not the case if you take a look at the water in front of our dam in Kanchanaburi, right? And that's the realistic fluid. The laminar flow is a kind of fluid flow when adjacent layers of the fluid slide smoothly past each other, and turbulent flow is a kind of this is not the ideal fluid. Okay, it's not a property of the ideal fluid. Turbulent flow is a kind of the fluid flow when the flow becomes irregular and chaotic. In turbulent flow, there is no steady state pattern. Okay, the flow changes with time because the flow pattern continuously changes. Okay, but it's not our assumption here. Otherwise, it's going to be too difficult for the high school level. Or 605 มีคนลาไปด้วยนะครับเขียนไหมก็จะประมาณนั้นโอเคwho else yes the ผมแชร์หน้าจอยังนี่ผมไม่ได้แชร์เลยไม่มีใครว่าผมทำไม604ไม่แจ้งผมไม่ได้แชร์หน้าจอครับ my god ผมไม่ได้แชร์มาตั้งแต่ห้อง604แล้วครับเพราะมีใครดูมั้งผมว่าโอเคnow we arrive at the second topic in this section. Okay, here continuity equation. Okay, continuity equation talks about the conservation of the mass, okay, in fluid flow, and the conservation of the mass in fluid flow will give us an important relationship, and this relationship is called the continuity equation. Okay, continuity equation expresses the conservation of mass for an incompressible fluid, okay, flowing in a tube or some other channel, okay, in a fluid pipe, fluid hose, whatever type of the device the human uses. Okay, the continuity equation start from this simple figure. You have the input side here, and it's denoted by number 1. Okay, the location number 1, the first location, and you have the second location here. Okay, you have the speed at the second location v with subscript 2. You have the cross-sectional area at the second location is denoted by A with subscript 2, right? And at the first location, you have cross-sectional area. It's written as A with number 1, and V1 is the speed of the fluid flow in this area. Okay, and the amount of the thickness of the fluid layer here is denoted by this value, which is V1 times delta T. Okay, if you just consider only a small amount of time for the observation, you get the thickness here. The thickness here is also found by the product between V2, okay, the speed of this location, and the time of observation delta T. Okay, the product of AV is constant for an incompressible fluid. Okay, the water volume doesn't change. It means the incompressible fluid. So, product of A and V is constant for in this scenario, and we could use the continuity equation and solve for it. Okay. Let's move to the next figure. This is the figure taken from the book number 2, and here is the same diagram. taken from the book number 1. It just explains everything, exactly the same thing, but with different variables. The volume here, the thickness here is delta x1. Okay, delta x1 is that value. Okay, delta x1 is equal to v1 times delta t, and delta x2 equals v2 delta t. Okay, and yeah, that's what we could do. Okay, at this location, of course, it has its own cross-sectional area A1, and here we have cross-sectional area denoted by A2. Okay, fluid moving with the streamline flow through a pipe of varying cross-sectional area A1 to A2, right? From A1 to A2, and yes, volume flow rate through A1 must equal the rate through A2. So A1 V1 equals A2 V2. That's the continuity equation. Okay, yeah, it says that the amount, either in terms of mass or volume of fluid flowing through a cross section of the tube in a given time interval. Time interval means delta t. Okay, delta t here must be the same for all cross sections. Okay, for whether you are here at the number 1 end or the number 2 end, right? Or even you want to observe it here in the middle, wherever in this pipe. Okay, the amount of fluid flow will be the same. Okay, fluid flow rate. Okay, and from this expression, we're gonna have delta V by delta T. This is the flow rate. Okay, the volume of the fluid flow per time, it's called flow rate. Okay, volume per time, and it's equal to A1 V1 times A2 V2. All right, times A2 V2 right here, and provided that the fluid is incompressible and there's no leak in the tube. Okay, there's no hole at all in this water hose or water pipe. And yes, the product AV is the volume flow rate. Okay, it's the flow rate in terms of volume. And another way is that you just multiply this one by the density, the rho, right? The density rho at both sides. You would get what is that? If you express the rho as delta m by delta v, right? You're gonna have here. You would have here delta m by delta v, and you would have here delta m by delta v. So with the expression, you would get the right hand side is solely rho, right? This one you're gonna have delta m by delta t, because delta v cancel each other, and you get delta m by delta t. You get rho and a and v on the right hand side here. Okay, that's the product of the flow rate. But in terms of mass, okay, if you take a look at this, the unit for delta m by delta t is going to be kilogram per second, because the unit of the mass is kilogram. Unit of the time is second, so rho is kilogram per cubic meter, and here is square meter, and this one is meter per second. So totally you would have here kilogram per second, right? It's flow rate in terms of mass, or simply called mass flow rate. Okay, let's start with the first example about the continuity equation. You have here the water, each second 5,525 cubic meter of water flows over the 670 cliff of the let's get to our point, the this one. Okay, we are talking about the waterfall which locates in between the border between in the border between Canada and the United States. It's called Niagara, and that Niagara, we have the so-called Niagara Fall, and in this fall there are sub areas. One of these is the Horseshoe Fall, right? Horseshoe Fall portion of the Niagara Falls. The water is approximately 2 meters deep, and it reaches the cliff. Estimate its speed at that instant. So let's summarize it. You have this is the cross-sectional area of the Horseshoe Fall. The height here is 2 meters, and you have here the width 670 meter. Right, this is the cross view of the water flow in this Horseshoe Fall, and they just go up. They just flow to us, right? And they say the water flow rate here. Okay, if you take a look at they measure the flow rate, the whole volume of water per second, as 5,525. Okay, it's less. It's right. It's somehow it's less than 1 ton, right? Oh, it's more than 1 ton. It's 5 ton per second, right? 5.5 ton. So it's a big amount of water flow actually. It reaches the cliff. Okay, it's the water will fall down to the lower position. Okay, lower position here. And yes, the first question is there is only a single question, right? Yes, estimate its speed at that instant. Okay, what is the speed? So it just flow in this way, right? What is the speed at this location? And speed is v, right? So they want to know v at this location. Okay, มีใครจะเข้าที่ซูมอยู่ครับผมพยายามชำเลืองมองอยู่นะ Okay, yes, we will try to compute the speed of the water flow in this at this scenario. All right. What tool should we apply to this problem? Yeah, we have just learned only the continuity equation, right? It say that. Oh, sorry. อ๋อนะครับพออากาศเปลี่ยนครับฤดูเปลี่ยนครับผมก็จะมีอากาศทางเดินหายใจนิดนึงครับ Sorry for that. The water flow rate is 5,500, right? Cubic meter per second, and we know the cross-sectional area. Right. Yes, the tool that we have just learned is only the so-called continuity equation. Continuity, right? Equation, which says that there will be the volume difference per time difference equals the cross-sectional area at one location times the speed of the water flow at that location equals also to another is also equal to another cross-sectional area at that location and the speed at the second location. Okay, but from what we have seen here, we know only the height of this water flow and the width of this water flow. Okay, let's say we just measure the width in a straight way, but actually it's not a straight line, right? Let's say the total distance, okay, if you walk around here, it's 670 meter. Okay, and yes, the height, okay, of the water from the water level to the ground at this location is approximately 2 meters. So which one should we use? Okay, of course what we could use is only this one, the continuity equation. This is the only tool we know. You know that 5,525 is the water flow rate in terms of volume, right? So it's gonna be this one, right? We will use this relation as we know that delta V by delta T is 5,525 cubic meter. Oh no, with the power of 3 per second, right? That's the water flow in terms of volume. Okay, and A1, right, which is the cross-sectional area. Yes, of course, it's a rectangular form, right? We need to find cross-sectional area here. This one is 2 meter, and here is 760, right? 760 meter too, right? 67. I'm sorry. This one is 670 meter. So the cross-sectional area is gonna be the product between width and height, right? It's gonna be width times height of the water, right? And yes, it's I'm not sure about my English. ไฮนี่มันมีนี่ป่ะwhere is the mouse? Yes, it's already correct. Okay, width is 670 and height is number 2, right? It's gonna be, what is that? It's 1340 square meter, right? Okay, we know A1, right? We know delta V by delta T, which is this number, and we want to find V1, right? The speed of the water flow at that location. We're gonna move A1 in this relation to the left hand side. So V1 will be 1 by A1, right? Times delta V by delta T. Or simply speaking, you have delta V by delta T divided by A1, right? Yeah, you would have the numerator as this value 5,525, and you have the denominator as 1,340, and this one, right? And you could put it into the calculator, right? You're gonna have speed 51340 and no like that ทำไมมีเครื่องหมายอันนี้here 41231 right 4.1231 it's approximately 4.1231 and velocity is in meter per second right and that's it for the velocity of the water flow in this horseshoe fall, right, which is a part of Niagara Fall. Okay, we have got the speed of the water flow already. It's around 4 meters per second. And what about this value in terms of kilometer per second? We have to multiply this value by 3.6, right? 3.6 is around 15 kilometers per second, right? And you know that 15 kilometers per second is like you ride a bicycle and the speed of your bicycle is around 15 kilometers per second, right? It's a little bit faster than how you walk, right? Yeah, that's the answer for the first example about continuity equation. Now we arrive at the second example about continuity equation. ขออนุญาตเคลียร์จมูกนิดนึงครับมีปัญหาเรื่องทางเดินหายใจครับ Okay. In the second example, we have a complicated scenario. Given 1 liter be 1,000 cubic centimeter, right? 1,000 cc. Okay, 1 liter is equal to 1,000 cc or cubic centimeter. A water hose is 2.5 centimeter in diameter. It is used by let's draw it. It's here the cross sectional view of the hose and diameter is 2.5 centimeter. Okay, and it's used by a gardener to fill a 30-liter bucket. Okay, and the gardener notices that it takes 1 minute to fill the bucket. Okay, let's draw what's going on in this. In physics, please try to draw something happens, okay, in figure form so that it's easily understandable. Okay, you have okay, this is the first scenario. Okay, first scenario, water hose. Okay, a gardener, right? This guy, this is the gardener, and he carry the water flow like that. Okay, he carries the water flow, and okay, the water just get into this pipe, right? This hose, flexible or made of silicone or something like that. The water is gonna go, and he just leave this this amount of water into a bucket. It's called bucket. It's the container. Okay, let's say it's whether it's made of metal or plastic. It doesn't matter. And the water get into this bucket, and it has the volume of 30 liter. Okay, 30 liter, and it takes T delta T is 1 minute. Okay, 1 minute, like that. Okay, yes, that's the first scenario in okay, the now in the second scenario, in the second scenario, we attach the nozzle to this one. To this hose, okay, the same hose, but we attach a new thing into this water pipe. It's called nozzle. Okay, it's a piece of we made of metal or something like that, and this nozzle, okay, actually it should have gradual shape, right, like that. And yes, and the water is gonna flow out of this nozzle, and yes, there is no bucket at all, right? They just left the water flow, and yes, we have another. This is the ground. Okay, this is the ground, and of course the water will flow like this because of the because the earth has the gravitational force acting on the water streamline, right? So the water flow or the water drop, so the water is gonna fall down onto the ground, right? And what they say is the nozzle is held so that water is protected horizontally. Okay, the nozzle is parallel to the ground. Okay, and 0.1 meter above the ground. Okay, so the height here is 1 meter above the ground. All right. Over what horizontal distance can the water be projected? So they want to know the distance here. Okay, what is the distance at this location? Okay, what is the distance of the water? Oh, no, I'm stupid. No. The distance is measured from this point. Oh no, the distance is measured from the starting point of the water out of the nozzle, right? So it's gonna be here. What is D at this location? Yes, we get the distance here, and the battery of the my phone is very minimal. Oh no, it's turn this off already. So the distance d is what they want to know. Okay, how far from the nozzle the water is going to drop or reach the ground. So we need to know this quantity, right? That's the second scenario. And yeah, this is the information from the first scenario, right? And the tool we have is only the continuity equation, right? We know only the continuity equation. So how could we solve this problem, right? Yes. Okay, let's go ahead simply, right? The tool we know is only continuity equation, and continuity equation says delta V by delta T is A1 V1 equals A2 V2. Right. So let's talk about the main something that you need to know is that the water flow in both scenario will be the same, right? The water flow in this scenario should be the same as the water flow rate in the second scenario, because it comes from the same source of the same water pump. Okay, the same water pump would give you the same water flow rate, right? Whether in terms of mass per second or cubic meter per second. Okay, the same flow rate because you have used the same water pump. All right, so yeah, that's the linking information from between those scenarios. So now we will determine some information from the first scenario. Which one? They don't provide even the cross-sectional area of the hose. The speed is also unknown, right? So what we could know from the first scenario is only this amount, right? The volume change per time difference, right? So it's gonna be delta V by delta T equals 30 liter, right? Times 30 liter. What is that? They say 1 liter. 1 liter equals 1,000 cubic square meter, right? Cubic square meter. And if you convert this one to cubic meter, it's gonna be 1,000 times 10 raised to negative 6, right? Cubic meter. And it's actually 10 raised to negative 3, right? Cubic meter, right? That's what we could change, right? From 1 liter to cubic meter, right? So this one is gonna be 30 liter. If you convert it to cubic meter, you have to multiply it by 1 10 raised to negative 3 and cubic meter per time, right? Per time. So they say it's 1 minute, right? It's 1 minute. It's 1 minute here, and if you know it's what is that in second? It's 60 second, right? 60 second. So in standard form, if you calculate this, it's gonna be what is that? It's 1 by 2, 0.5, right? 85 times 10 raised to negative 4, and it's cubic meter per second, right? Cubic meter per second, that's the water flow rate. Water flow rate in terms of volume. Okay, that's the left hand side of the continuity equation that can be derived from the first scenario. All right, so in the second scenario, let's try to determine the distance here. Yeah, we know the water flow rate from the hose or the water pipe here, and they say the cross-sectional area of the nozzle is 0.5. Okay, a nozzle is 0.5 square centimeter, but we need to convert it to the SI scale, right? The standard international unit, right? What it is equal to 0.5 times 10 raised to negative 4 cubic, square meter, right? Yeah, that's the area of the nozzle in square meter, right? And what could we do if we know the area of the nozzle? Yeah, let's apply the continuity equation. We know that delta V by delta T is equal to A1 V1, right? Yeah, let's use this relation again, as same as the example about SMS the example about the Niagara Falls. We're gonna use this example. We're gonna use this relation. As we know, on the left hand side, delta V by delta T equals the cross-sectional area A1 and V1, right? We know A1, which is the cross-sectional area of the nozzle, right? But we don't know V1, the speed of the water out of the nozzle, not out of the hose, okay? From the nozzle. So we want to know V1 because we know the water flow rate, which is 5 times 10 raised to negative 4 cubic meter per second here. Okay, we have to solve this equation for V1. V1 will be, again, 1 by A1 and delta V by delta T. And of course, you would have delta V by delta T divided by A1, right? And of course, the numerator is the water flow rate, which is 5 times 10 raised to negative 4 divided by A1, which is the nozzle area, cross-sectional area, 0.5 times 10 raised to negative 4, 2, right? And we have to open a new page right now. Yes. From this calculation, okay, the division here, you get V1 is simply number 10, right? Oh, but the unit of the speed is meter per second, right? Yeah, that's the speed of the water getting out of the nozzle here, 10 meter per second. And what else? But our target is the distance here, right? And as you know, the speed of the water at any location down in this curve, right? This is the projectile motion actually. It has two components. The movement along the x-axis, this is called Vx. and it has also the movement along the y-axis, which is called Vy, right? Vy at any location. But for us, let's consider the movement along the y axis, okay, in the vertical way. Let's consider let us consider the motion of the water flow along the y-axis or in the vertical way. In the vertical way, right? You know that the water just start from here and it just drop right to the ground, okay, like this. It start because there is no velocity along the y-axis at all, so uy here is 0 meter per second, right? It just reach with Vy, right? But it's unknown, right? We don't know the final speed once it reaches the ground at this location along the y-axis only, okay? And we know that this is the time, right? We don't know the time that is going to be used or consumed at this state, right? We don't know the time for the water drop to reach the ground, so we need to determine the time that is consumed by the water drop from the nozzle to the ground, right? Yes. But this is the motion that is forced by or is regulated by the acceleration, right? Because there is a force acting all the time to the water drop or the water flow here, right? And that acceleration is this one. It is g, okay? G is the acceleration that always take place with this water drop or water flow, right? So from your Mathayom 4, which from your Mathayom 4, what formula do you have in Mathayom 4? Yes, you have in the first year of your high school, you have where is that? V equal U plus AT, right? You have V square equal U square plus 2AS, right? And you have another one, which is S equal UT plus 1 by 2 AT square, right? Those are basic formulas regarding the motion, right? That has acceleration when there is also acceleration in that movement, right? Yes, we have these three fundamental equations, right? And we are gonna apply these three equations to solve for t, right? We know uv, right? What we know, the quantity that that is known to us is, we know the acceleration, right? We know the acceleration, which is g, right? We know the distance, right? The horsel is 1 meter above the ground. We know the height, which is the distance. We know the distance. Oh no. We know the distance, which is h, which is the height. We know the initial speed, right? Initial speed, which is uy equals 0. Uy equal to 0. And what else? We want to find the time, right? Time is unknown. Unknown variable is time. So, which formula should we use? Okay, which formula should we apply to? We g acceleration is right here. Everyone has a, right? H the distance, which is the letter s. Okay, these two. Initial speed, both have initial speed, but time. Okay, we want to find time. So the one that most coincide with our target is this one, right? S equal to ut plus 1 by 2 at squared. S equal ut plus 1 by 2 at squared, right? And yes, we know that s is going to be sy, which is h, right? H equals 0, right? Uyt is 0 plus 1 by 2 a is d, right? And t squared is like that. And you're gonna solve this equation for t because we want to find time. And time will be, you move to number 2 to the left hand side, you move g to the left hand side and take the square root. It's gonna be square root of 2h by g, right? And yes, we substitute these two variables into this expression. T will be the square root of 2 times h, right? H is the height, which is number 1 here, right? 1 meter, okay, and number 1 divided by g, the acceleration is 9.8, okay, and you just put this calculation into the calculator, right? This ratio into the calculator, you're gonna get, is that correct? Yeah, 2 by 9.8. It's equal to 45175. 45175. 45175. The unit for time is second. Okay, the time that the water consumed to reach the ground is 0.45 seconds approximately, okay? And that's the motion along the y-axis, okay? But it's not what we want, okay? We want to talk about or consider the motion along the y-axis because we want to find the distance from the starting point here in the horizontal way, right? So now let's consider the motion of the water flow along on the horizontal way. Let's consider the motion of the water along the horizontal way yeah and yes you start here from the initial speed which is 10 meter per second, right? This is the speed along the y-axis, okay? Because they say the nozzle is placed vertically, the nozzle is placed in parallel to the ground, so this is horizontal, in a horizontal way, right? Completely in horizontal way. And yes, but there is no force acting onto the water drop in the horizontal way, okay? There is no force acting on the water drop in the horizontal way at all, right? There is only a force acting on the water drop in the vertical way, which is the gravitational force caused by the Earth or our planet, right? So when there is no force acting on the water drop here, we need no use. We need not to use this equation anymore, right? These equations, because these equations involve the acceleration, but we don't have acceleration along the horizontal way, right? So we're gonna use a simple motion equation, right? It's called V equal h by t, right? And we wanna find the distance d, right? Right here, what is d, right? And the speed here in this motion is Vx, right? Vx is 10 meter per second, right? And if you want to find d is actually h in this expression. You have to move t to the left hand side, right? Once you move t to the left hand side, you're gonna have d, which is s actually is the multiplication of v along the x-axis on horizontal way times the delta t, right? The delta t that you have just found is 0.45, right? So Vx is 10 meter per second times the time, right? Which is 0.4517 blah blah blah. I don't know, 175 second, right? That's t, and you times 10, you're gonna have 4.5175, and here is meter, right? And that's the distance which is far away from the starting point, okay? The distance far away from the starting point of your nozzle, okay? And the water is gonna reach the ground, okay? So this problem is quite complicated, right? But it's not beyond your ability, right, to observe this, right? Okay, and yes, now let's move to the next topic. Let's move to the next slide. Okay, let's check whether our calculation is correct. There is 4.5 blah blah blah, 4.515175 meter, right here. Okay, ก็ถูกอยู่นะครับ and now let's let's move to the next the next story. It's called Bernoulli's equation, right? Bernoulli comes from the word Daniel Bernoulli. So this person is Swiss, and he is a physicist. One of his work in 1738. Okay, his life is around 17,000 to 1782. So it's 82 years of age. He's 82 years of age, right? That's his life. Once he was 38, he discovered something, and this relation is known as Bernoulli's equation. He found that he found the expression about the pressure of the fluid to its speed and elevation. Okay, you know elevation, the amount of the height above any reference level, right? Bernoulli's equation is well known and is a consequence of energy conservation as applied to an ideal fluid. Okay, let's say again that we have to take into account the ideal fluid. Okay, to derive the Bernoulli's equation, we again assume the fluid to be incompressible, to be non-viscous. Okay, not incompressible. What does that mean? The volume cannot be compressed, and it has no friction among several layers of the fluid, and the fluid just flows in a non-turbulent sense. What does that mean, non-turbulent sense? It has no circular motion. Okay, it just flow in the straight way, in the straight line manner, and it just flows in a steady state manner. What does that mean? The speed doesn't change with time. Okay, the steady state, it means the speed doesn't change with time. It has no change of the speed with respect to time. Okay, that's a very, very simple way of motion of the fluid, right? Otherwise, we cannot choose the simple formula of the Bernoulli's equation. You have to deal with the integration version of the Bernoulli's equation. You have to use the calculus version of the Bernoulli's equation. But those are beyond our level in the high school level or the secondary school level. Okay, it's too complicated. You will meet those formulas in bachelor degrees, I think, yes, in physics or something like that. Okay, once you have enough background about calculus, okay, you will see that. Okay, there are two major forms of the Bernoulli's equation. The first one is this one. Okay, it means for any points along the flow tube. Okay, location 1, location 2, you have P1. Okay, the pressure at the first location. You have Y1, the elevation at the first location. You have V1, the speed at the first location, and you have P2, the pressure at the second location. You have Y2 at the second location, which is the elevation or the height in the second location. You have V2, the speed at the second location, and that's the first form, right? The summation of the pressure at the first location equal to the pressure at the second location. And Bernoulli's equation has another form. It means the summation of all these three pressures remains constant. Okay, it remains as a single value, which is a constant. And that's the second form. And now let's get into the detail of the Bernoulli's equation. What is the meaning of Bernoulli's equation if you don't go into the detail of this expression? Bernoulli's equation states the sum of pressure P the Bernoulli equation states that it is the summation of all three terms. The first term is the actual pressure. The second term is the kinetic energy per unit volume, which is a kind of pressure actually. Okay, energy, kinetic energy per unit volume, which is this term, right? And potential energy per unit volume, which is this term, right? It has the same value, okay? It has the same value for any location in that streamline, okay? It is the same for any points in that streamline. The Bentley effects refers to, okay, Bentley effect is a special case from the Bernoulli equation, and this effect is quite well known in fluid motion or in fluid dynamics. And the decrease of the static pressure in fluid flow will result in the increase of flow velocity due to energy conservation. If you don't understand this sentence, let's get into the detail. This is the figure about, this is a sketch of the fluid flow, okay, from the input here, number 1, to the output, number 2 here. And at the input side, you have the cross-sectional area denoted by A1. And A2 is the cross-sectional area in the second state, in the second location, denoted by A2. You just drill this pipe and you plug it with the barometer, which is a device to measure the pressure, the first one and the second one here. What you could observe is, of course, there is a speed V1, right, flowing from the left-hand side to the right-hand side. This is the larger side of the pipe, right, and what you could observe is the higher pressure P1, right. The needle of the barometer is pointing in this direction, right. And at this look at this pipe, right, you could see the needle of the direction of the needle is pointing in this way, okay, which is lower than this value, right, the first pressure. And yeah, what you could observe is the vector, the length of the vector V2 is longer than, is greater than the length of the first vector V1, right. And yes, you could see that when you have smaller pipe, okay, with smaller cross-sectional area, you get lower pressure, but you have higher speed at this location, okay. That's the relationship. Once you have bigger cross-sectional area, you have a lower speed, you have a higher pressure, like that, okay. And there you get it in realistic figure, right. This is the real measurement. You let the air coming in and the air is going out, whether it's the air or the water. And yeah, we drill a hole, we plug the barometer to this location, we plug another barometer to this location. Sorry for that. ขออนุญาตจำนิดนึงนะครับ sorry มีน้ำมูกนิดหน่อยนะครับโอเคแต่ว่าไม่ได้เป็นโควิดนะครับมันเป็นโรคแพ้จากอากาศครับโอเคเนื่องจากอากาศมันเปลี่ยนครับโอเคthat's the realistic figure, right, from the ideal figure here. And what you could see is that the direction of the needle here in this barometer is pointing to number 5, right, but this one is pointing to somewhere between 4 and 5, right. It's like a 4.5 bar, right. So this one has lower pressure than the initial one, right. You have bigger cross-sectional area. You have lower cross-sectional area here, but you have higher speed in the smaller tube, right? This is the cross-sectional view of the pipe. Okay, and if you don't believe this figure, you may take a look at another figure. And this one is just the glass, right? The glass which is clearly visible. And you drill the hole here, and you drill the hole here in the smaller end, in the smaller pipe. You connect it with U-shaped pipe, and you fill in the liquid here, okay, which is easily noticeable in red, okay. When you let the air or anything flow, let's say it's air, right? You let the air flow from left to right. The air is gonna flow from left to right, and you could see that here you would get really high pressure, and you would have really low pressure here. High pressure means the ability to push down the liquid at this side, and you would have lower pressure right here. At this side, the air cannot push the fluid down, okay, because they cannot do it comparing to this side, right? This side has higher potential to push the liquid because it has higher pressure. So you could see that the level of the fluid is different. Okay, this one has lower level of the fluid because it has higher pressure. All right. Yeah, that's the version without barometer, and this one is simple, right? They just show it, show the two pressures in numerical way, okay, from the scale on the barometers, right? Here you have another explicit, okay, another application which is explicit version of the water flow, okay, of the Bernoulli effect. It's the aircraft, okay, and here is the cross-sectional view of the wing of the airplane. Yes, once it flies above the air, above the ground, right, in the air. This is a sketch of the air streamline, and you have the air streamline under the wing. You have the air streamline above the wing, and you have higher pressure here at this location. You have lower pressure at this location. The speed of the wing would be higher in this area because you have more distance for the air to travel. Here you have shorter distance for the air to travel. That's why the air needs to have higher speed at this location. Once it has higher speed, it should have, or this area should have also lower pressure. And this area, once it has shorter distance, it has a lower speed, but it needs to have higher pressure, okay, to compensate this summation. And when it has higher pressure, if you multiply the cross-sectional area here under the wing, you're gonna get lifting force, and the lifting force is used to lift the whole airplane. Okay, that's the principle from the Bernoulli effect. Nearsighted. Now we arrive at the first example of the Bernoulli equation, but SMS M604. Okay, we cannot complete the first example about Bernoulli equation at all. Okay, but anyway, just go ahead with that. A nearsighted chairlift fires at a cattle rustler with his trusty six-shooter. It's a kind of gun, I think. And fortunately for the rustler, the bullet misses him and penetrates the tire water tank, causing a leak in figure 68. Okay, figure 68 like this. If the top of the tank is open to the atmosphere, determine the speed at which the water leaves the hole. When the water level is 0.5 above the hole, okay, water level is 0.5 above the hole, the broken hole here, okay. Where does the stream hit the ground? On the speed at which the water leaves the hole, okay. The first quantity is what is V1. The second quantity is what is the distance apart from the hole here, okay, along the x-axis, okay. We're gonna need to determine that. Let's draw the whole thing that happens in this problem. Yes, I believe, right? We have here a water tank of the town, and here is the water level, right? And this is the cattle rustler, right? Like it's the kind of thief, right? Who steal the cow and so on. And this is the sheriff in a short distance, right? Sheriff has a gun. I cannot draw the gun wheel, okay. This is the gun, okay. And the gun will fire the piston, right? The piston is going to get out of this one. But unfortunately, this piston misses the head of this person, of this laser, and it just hit the water tank, unfortunately, okay. It just hit the water tank, and this caused the water hole. This caused the water hole like that. So the water is going to get out of this hole, okay, and the water will flow in the projectile way, right, in the projectile motion. And the first question just asks us to find the initial speed Vx of the water flow in this location. And the second question just asks you what is the distance here, okay, how far the water is going to drop from the wall of this water tank or the hole here, okay. So we want to find two quantities from this problem, right? And in order to solve this is water, right? In order to solve this problem, you need to know something, right? The height of the water here is water level above the hole is 0.5 meter, right? 0.5 meter. And okay, they also say that the top of the tank is open to the atmosphere, so there is a pressure caused by the air here, which is PATM, right? And yes, we are gonna apply the Bernoulli equation, right? He said Bernoulli equation says P1 plus rho G Y1, right? Plus 1 by 2 rho V1 square equals P2 plus rho G Y2 plus 1 by 2 rho V2 square, right? Yes, we assume that this one just located in sea level. We have almost the same pressure caused by the air, okay? Pressure caused by the air here, even it is 0.5 meter under the water level, we assume that P1 is approximately equal to P2, and it's equal to P ATM. Okay, the air pressure is exactly the same, is approximately the same for both locations, so we don't need to take into account this term at all, right? Both are equal to each other, right? Unfortunately, time is over now. Yes, หมดเวลาแล้วครับก็ we are going to continue this example next time on Friday. Okay, see you later, or let's capture the screen of anything that happens. Okay, we will continue this example next time. Okay, in the lecture on Friday. If you have any question, just let me know. Okay, if you are not clear about anything, just ask me by phone or by typing. Okay, Lavipon is in the YouTube channel, which is in YouTube channel, right? In Kitiwat, I think Kitiwat is from M605, if I can remember. Kitiwat นี่น่าจะห้อง605ครับ Okay, today we will quit the lecture right now because the time is so. You need to take rest, right? For 20 minutes before the actual lecture time. Okay, สวัสดีครับบ๊ายบายครับThree, two, right. Okay. Switch. Yes.